After our considerations regarding rationale for atom sizes and associated discussions, we're now in position to proceed in depth at our main intention for Chapter 23, establish basis for rationalizing strengths of Bronsted-Lowry acids and bases. You will see that what we shall do is to consider methods like charge to size ratio, electronegativity, and other things which we'll put into our grab bag of considerations, which will allow us to establish a rationale for effective negative charge density of a given Bronsted base. Because as we know from conjugate theory, once we have a handle on the strength of a Bronsted base, then immediately we have a handle on its conjugate acid. So for a given collection of acids whose strengths we'd like to rationalize and compare on a relative basis, we will aim at rationalizing the effective negative charge densities for the conjugate bases of these acids. Because after we have established such, then we'll know the strength order for the conjugate acids of these bases. Now, just because it's an extension of the idea of electronegativity, or atomic property of electronegativity if you wish, we talked in brief about orbital electronegativity, reminding you that as far as atomic orbitals are concerned, for a given energy level, electrons will always reside preferentially in s orbital, followed by p, followed by d, and ultimately and lastly followed by f. Now, as it turns out, we really don't much care about electron density in f orbitals, because f electrons and f orbitals are rarely part of the valence environment of an atom. More on that later. Now, if then s orbitals as atomic orbitals have the highest orbital electronegativity, that's our conclusion. That's where the electrons are more stable relative to p or d, like the 3s, 3p, 3d orbitals in energy level number 3. Then it follows for a hybrid orbital. The hybrid orbital which has the greatest orbital electronegativity will be the hybrid orbital which is highest in s character. So, if we recognize that hybridization is just a game, it's an idea we cooked up to help us understand bonding properties, or in this case, Bronsted acidities. Then, if we take a look at all the possible hybrids derivable from the orbitals, atomic orbitals of energy level number 3, 3s, a single orbital sublevel, 3p, a 3 orbital sublevel, and 3d, a 5 orbital sublevel, we can cook up a whole series of hybrids, going from sp, where we mixed up one s orbital with one p orbital, followed by sp2, where we mix up one s orbital with two p orbitals, all the way down to sp3d5, where we have mixed up all the orbitals from energy level number 3. And, based on what we've already recognized, it follows that the sp hybrid will be the hybrid of greatest orbital electronegativity for hybrids derived from the atomic orbitals of energy level number 3, because sp is 50% s character. All the way down to sp3d5, which has the lowest orbital electronegativity for hybrid orbitals derived from the atomic orbitals of energy level number 3. Because that's only 1/9 S in character. To make an sp3d5 hybrid, we have imagined to mix up 3s orbitals with all the p orbitals and all the d orbitals. So, since that has the least s character, it will be the hybrid orbital of lowest orbital electronegativity. Now, how can this idea help us to rationalize Bronsted-Lowry acid strengths? Well, I left you with these two molecules and recognized, this was the conclusion of yesterday's conversation, since these nitrogen atoms are sp3 hybridized and these nitrogen atoms are sp2 hybridized, we have an idea why the double bond is stronger than the single bond, or the covalent bond interaction between the nitrogen atoms. Because the sp2 hybrids are 33 1/3% S character. The sp3 hybrids are 25% S character. Upshot, the sp2 hybrids stabilize bonding electron density to a greater extent than sp3 hybrids. The more effectively you stabilize bonding electron density, the stronger bond and the shorter bond. The stronger bonds are generally shorter bonds. In this case, it has to be true because the atoms in consideration are all the same atom, nitrogen. Now, both of these are very weak acids. For example, do you see an immediate similarity of these molecules to ammonia? What's the similarity? Well, ammonia is composed strictly of a nitrogen atom and hydrogen atoms, like these molecules, except these each have 2 nitrogen atoms. But they're each derivatives of elemental nitrogen and hydrogen, no other elemental components. Do you expect ammonia to be a reasonably strong Bronsted acid? Have we considered it in such fashion when we were in chapter 18? No. Ammonia is a lousy Bronsted acid. These molecules are also lousy Bronsted acids. But after this consideration, you'll recognize why we could argue that either of these molecules are stronger Bronsted acids than ammonia. None of them are strong acids by any stretch of the imagination, and we'll also recognize why this molecule is a stronger Bronsted acid than this molecule. Now, we said we're going to do this. We're going to achieve this rationale, or basis for rationale, by looking at assessment of effective negative charge densities on the conjugate bases of the acids in question. So I'm going to take away one of these hydrogens as H+, which creates a negative charge on this nitrogen atom. I'll take away one of these hydrogens as H+, which creates a negative charge on this hydrogen atom. And if you wanted to sketch ammonia, you'd take away one of the H atoms as H+, and you'd have a picture of the amide ion, H2N with minus charge. How do these bases compare strength-wise? What is your expectation? In each case, we've got a negative charge parked on the nitrogen atom. And in each case, the nitrogen atom in question is covalently connected to another nitrogen atom, which in turn is connected to single H atom or 2 H atoms. But focus your attention on the nitrogen atoms, where the negative charge has been created. How is this atom hybridized? sp2. And this atom? sp3. Which of these is the hybrid orbital of greater S character? sp2. So which of these nitrogen atoms stabilizes negative charge density more effectively? sp2 atom. Did we not start this conversation yesterday by my reminding you what is a working definition of electronegativity? A measure of the ability of a bound atom, a covalently bound atom, to stabilize negative charge density. Well, now we're looking at it from an orbital electronegativity standpoint. The sp2 nitrogen is a nitrogen atom of greater orbital electronegativity and therefore stabilizes this negative charge more effectively than this nitrogen stabilizes its negative charge. What does that mean about the relative reactivities of these bases? If this negative charge density is more stable than this negative charge density, which one of these bases, 1 or 2, is the more reactive base? 1. So the more stable base, number 2, is the weaker base, right? It's more stable, less reactive. Well then, if we put back the H pluses and regenerate the parent molecules, which is the stronger acid? The one which is derived from the weaker base. That part of acid-base strength consideration we talked about in chapter 18. The stronger is a Bronsted acid, the weaker, more stable, less reactive is its conjugate base, and vice versa. Conjugate base of this is a weaker, less reactive base than the conjugate base of this, which at the same time means this is the stronger acid. Now I told you, if you think carefully about this, you'll realize why ammonia is a weaker acid than either of these. They're all very weak acids, as we've already noted. Well, what I'm telling you is, with that statement, that the amide ion, is a stronger base than both of these. Well, this nitrogen, if you write out the entire Lewis structure, will be found to be sp3 hybridized like this nitrogen. So you see a similarity of this nitrogen to this nitrogen. sp3 hybridized. So now you're going to have to go beyond orbital electronegativity to make a decision why this base let's put it back here. Why this base is a stronger base than this base. Orbital electronegativity is not the deciding factor because these nitrogen atoms are each sp3 nitrogens, each with a single unit of minus charge. Well, if the answer is not immediately obvious to you, I'll provide you with this clue. The answer depends on an extension, an additional application of the idea of electronegativity. It's called induction. We'll be there soon. So back to this when we get there. Now, regarding assessment of effective negative charge density on the basis of charge to size ratio, which is why we talked about all this size stuff previously, versus electronegativity. And now we've added orbital electronegativity. So our three considerations so far in our grab bag of ideas that we will use as necessary to rationalize strengths of Bronsted acids. Charge to size ratio, which obviously relates to size, electronegativity, orbital electronegativity. Consider two hypothetical atoms, X and Z. Let's imagine these atoms are about the same in electronegativity. Practical example, real example, chlorine and bromine. Chlorine has an electronegativity of 3.0, 3.1 on some scales, bromine 2.8. They're atoms in the same family, family 7A, and ever so obviously they have similar electronegativities. How do these atoms compare size-wise? Remember the size stuff we talked about? Are these A family atoms? And what we recognize is that when you compare the size of atoms, which are a family, and from the same family, as you go from period to period within the family, what do you observe size-wise? Big increase in size. Bromine size-wise is a lot larger than chlorine. So let's imagine that hypothetical atom X and hypothetical atom Z each collect an electron and become anions. X minus, Z minus. If X minus is derived from X, which is a lot larger than Z, then we shall expect X minus to be a lot larger than Z minus. Now, let's take these anions derived from atoms X and Z and add H plus to them. Then we make HX and HZ. Which of these do you expect to be the stronger acid? Which one? For starters, which factor seems to matter more in this assessment? Charge to size ratio to assess effective negative charge density, or electronegativity? Which factor? Charge to size ratio. Big difference in size, but the atoms are, but the anions are derived from atoms that are about the same in electronegativity. Okay so far? So tell me, if I imagine a baseball next to a soccer ball, and on the surface of the baseball I smear 1 unit of minus charge, and at the same time on the surface of the soccer ball I smear 1 unit of minus charge. So I have baseball minus and soccer ball minus. An anion derived from a baseball and an anion derived from a soccer ball. As a function of charge to size ratio, which of these imaginary bases, the baseball anion or the soccer ball anion, has the greater effective negative charge density? Baseball. Isn't it smaller? They're both -1, but for the much smaller baseball I've smeared the charge over a much smaller surface. Nothing fancy about this. So based on charge to size ratio, it should be obvious that the baseball minus has a much greater negative charge concentration than the soccer ball minus. Well, if we apply that to this case and recognize that Z minus has the much greater negative charge concentration, that means Z minus is the stronger or weaker base if it's got the greater negative charge concentration. Stronger base or weaker base? Stronger. It's got more negative charge concentration. That means this is the stronger acid, because the conjugate base of this acid, X minus, is the weaker, more stable base because it has been assessed to have a smaller negative charge concentration than this thing. All right, let's play another game. Now we're going to talk about imaginary atoms X and Y. Now, don't be puzzled by the fact that you see the symbol Y in the periodic table for yttrium. I don't mean this Y to represent yttrium. Now we'll imagine that atoms X and Y are about the same size. But X is much more electronegative. Example, nitrogen and oxygen. Nitrogen and oxygen are neighboring atoms in period number 2. From our size trend analysis, we recognize as you go left or right across a period, you observe a steady size shrink, but it's the case that as you go from atom to atom, the change in size isn't a whole lot. So oxygen is smaller than nitrogen, but not a whole lot smaller than nitrogen. But the electronegativity of nitrogen is 3.0, whereas the electronegativity of oxygen is 3.5. A good deal more electronegative than nitrogen. That's the real case. Back to hypothetical X and Y. On collecting an electron, X minus and Y minus will now be about the same size. Since they are derived from atoms, they're about the same size. Now we're going to add H pluses to these things and make HX and this time HY. Which shall be expected to be the stronger acid? HY or HX is the stronger acid? The answer to the question, of course, rests on which of these bases is assessed to have the greater effective negative charge density. Because the base which has the greater effective negative charge density is the stronger base. And its conjugate acid will be the weaker acid. Which of these is the stronger base? X minus or Y minus? The stronger base. Which one? X minus is derived from X. And X is more electronegative than Y. More electronegative. What again is this electronegativity property? It's a measure of the ability of a covalently bound atom to effectively stabilize negative charge density. So which of these anion species is more effectively stabilizing its negative charge density because of electronegativity? Which of these atoms or anions is derived from the more electronegative atom? X minus. That means the effective negative charge density is more stable on which? X minus. That's what electronegativity does. It stabilizes negative charge density. Isn't that what we did when we used this idea of orbital electronegativity for acids 1 and 2 at the top? Well, now we're even simplifying the idea. We're not talking about orbital electronegativity. We're now talking about a real property of atoms, electronegativity. And so, charge to size ratio. These species will stabilize negative charge density to about the same extent, because they're about the same size. But electronegativity, this species stabilizes negative charge density much more effectively than this species, because this species is derived from this atom, which is much more electronegative than this atom. That means this is the less reactive, more stable base, which means HX is stronger than HY. Keep in mind what electronegativity is. The more electronegative atom, or in this case, species derived from the atom in question, stabilizes negative charge density more effectively. Now, what if we are asked, with no information beyond what we have so far considered, to assess the difference in Bronsted acidity between HZ and HY? Can we achieve that? At this stage of the game, we cannot. Because if we compare HZ to HY, we shall expect, based on electronegativity arguments, that HZ is the stronger acid. But based on charge to size ratio, we'll expect HY to be the stronger acid. And since this is all the information we have, we can't make a decision. if Hz and Hy were real species at this point, if this is all the information we'd have about these, what would we have to do to resolve this issue? Hz versus Hy. If we really needed to know which one was the stronger acid, and this is all the information we have, what would we do to answer the question?
Go to the lab.
Go to the lab and make a water solution of each of these acids at the same concentration and observe pH. The solution with the lower pH would be the solution of the stronger acid. Now then, real cases. No more hypothetical imaginary stuff. And I trust at a glance you'll see how these real cases relate directly to what we've already talked about. HI, HBr, HCl, HF. Now in our acid-base table, we do not have HI and HBr contained. But we have HCl and HF contained. How do those acids compare strength-wise? HCl is a much stronger acid than HF. In fact, categorically, HCl is one of our strong acids, whereas, as our acid-base table tells us, HF is a weak acid. Now let's look at these acids. In our acid-base table, we have HF and H2O listed in the acid column. We have the ammonia molecule in our acid-base table listed only in the base column. And we've already argued that ammonia is a pretty weak base. Pardon me, an extremely weak acid. And then we'll put in the methane molecule. Because what we're here doing is to look at a series of acids on a relative strength basis, with the acids being derived from elements in the same family. Here we're looking at a series of acids on a relative strength basis, with the acids derived from atoms in the same period. Neighboring atoms of period 2, carbon, nitrogen, oxygen, and fluorine. But we know about these two acids strength-wise. Which one is stronger? So there's what we know so far. Now you learned about periodic trends and establishments thereof. Thank you, sir.
Yes, sir.
He did it. That's good. From what we have on the board, HCl is a stronger acid than HF. What pattern, what trend follows if we want now to put HBr into this consideration? Which acid would you expect to be stronger, HBr or HCl? HBr. Now, we know about HF being a stronger acid than water. So let's throw ammonia into the mix. How does the acid strength of water compare to the acid strength of ammonia? Which one is stronger? Water's stronger. So we can complete these trends, or relative acid strengths. There it is. And this is correct. I'm just giving you as an experimental fact. Now let's get at the rationale. Because when we know this is the relative strength of these halogen acids, then we know that F minus is a stronger base than Cl minus, which is a stronger base than Br minus, which is a stronger base than I minus. And for these we know that the anion derived from this, which is the methide ion, which Lewis structure analysis will show you, parks the minus charge on carbon, so I'll write it as H3C minus. is a stronger base than the amide ion, which is a stronger base than the hydroxide ion, which is a stronger base than the fluoride ion. All right, we know the facts. What explanation can we offer? As things stand, we've looked at charge to size ratio, electronegativity, and orbital electronegativity. I'll start simply by reminding you that orbital electronegativity will not be part of this consideration, because you will recognize, if you were to write the Lewis structures, that each atom on which a minus charge has been developed is sp3 hybridized. And they're all period 2 here. Well, maybe I shouldn't have said what I said. You could apply the idea of orbital electronegativity here, just like you could apply the argument of electronegativity here. But now let's get at the explanation. To explain this halogen acid trend, strength trend, because we now have the facts before us. So we better cook up an argument that fits the facts. Would you like to argue that fluoride ion is a stronger base than chloride ion based on electronegativity or based on charge to size ratio? What is your conclusion? Charge to size ratio, because you know fluoride ion is derived from fluorine, which is the most electronegative atom in the periodic system. So the electronegativity argument doesn't work. But we at the same time know that chloride ion is a lot bigger species than fluoride ion. Bromide ion is a lot bigger species than chloride ion. Iodide ion is certainly the largest of all of these and a lot bigger species than bromide ion. So with iodide ion, the weakest of these halogen bases, we have the largest spherical entity bearing a unit of minus charge. So from a charge to size ratio standpoint, this species, because of its size, dilutes the negative charge to the greatest extent. Dilutes the negative charge. Deconcentrates it. Makes it more stable. Makes this the weakest base. Now let's look at these. Charge to size ratio. Now keep in mind, when we went from F minus to Cl minus, big change in size. But when we go from carbon to nitrogen, not much change in size. From nitrogen to oxygen, not much change in size. From oxygen to fluorine, not much change in size. But a rather substantial change in electronegativity. Fluorine 4.0, oxygen 3.5, nitrogen 3.0, and carbon 2.5. Furthermore, independent of the presence of H as an elemental component of the hydroxide ion, how do you expect the size of this oxygen atom with a charge of -1 to compare to the size of our fluoride ion? About the same. But which one should be a little larger? This one, right? Doesn't that keep with our size trend? Carbon bigger than nitrogen, bigger than oxygen, bigger than fluorine. So as we go from Carbon to fluorine atom, we're seeing a steady shrink in size. Okay? Which means, if I try to rationalize the difference in the base strengths of these two species on the basis of charge to size ratio, I'm going to argue this to be the weaker base. And when I get to H3C minus, now carbon versus fluorine, pretty good difference in size, because now we've gone across 4 atoms. So clearly, this is a larger base than this, which means charge to size ratio would dictate this being a weaker base than this. But this is one hell of a strong base. This thing is a much stronger base than hydroxide ion. This thing as a base makes this as a base look like nothing. So charge to size ratio is no good for this argument, because that suggests this would be the weakest base of these in-period derived anions. But based on electronegativity, we expect this minus charge to be the most stable, because F minus is derived from F, the most electronegative atom. So based on electronegativity, I have a method for explaining why this is the weakest and most stable of these 4 bases, and now I'm right. So that's the argument I use. So note, if you have not yet, but I think you have, that the charge to size assessment of effective negative charge density and the electronegativity assessment of effective negative charge density, they oppose each other. Here, charge to size argument says this is the weakest base, most stable base. Electronegativity argument says this is the weakest, most stable base, and in this case, this is the weakest, most stable base. So the electronegativity argument fits the facts. Here, the opposite is true. Here, the charge to size ratio fits the facts, and the electronegativity consideration is in contradiction with the facts. Because here, based on electronegativity, I'm going to pick this as the weakest base. Wrong. This is the strongest base of these halide ions. When students first hear about stuff like this, they don't like it. They don't like it because they have not heard of arguments like this before. Up until now, a lot of what you've heard, if not everything, is this is the way it is. Well, now you're being programmed to recognize assessment, explanation of facts is often difficult, because you may have 2 or more considerations which apply, things you have to think about. Charge to size ratio, electronegativity. And they may provide opposite direction explanations. So we proceed. Induction. You will see that induction is nothing but an extension of electronegativity. You will see that as if by magic, electronegativity or electronegativity effects, I should say, are in fact exerted through a covalent bond skeleton for a species. If nothing else, this screams at us. Electronegativity is real, that's for sure. I have on the board sketched the Lewis pictures for 3 acids. Acetic acid, with which we are familiar. Now, before we talk about these acids, recognize that the acetic acid molecule has got 4 hydrogen atoms per molecule. But when the acetic acid molecule behaves as a Bronsted acid, does it ever develop a charge of -2? -3? -4? No. The only H which acetic acid molecule ever loses as H+ is This one. Why is that? If you take away one of these H's as H plus, you'll create a minus charge on carbon. What did this analysis tell us about the ability of carbon to stabilize negative charge density, given that carbon is, number one, reasonably small, and number two, not very electronegative? Those properties magnify negative charge density. So creating this species is practically speaking impossible, because this base is too damn reactive. Again, the only H which ever leaves the acetic acid molecule as H plus is the oxygen bound H, because now you've got a minus charge on the oxygen atom. And oxygen is an atom of considerable electronegativity, outdone only by fluorine in this property. All right? Now, alongside acetic acid, I've sketched the Lewis structure for trichloroacetic acid, TCCA, trichloroacetic acid. Why do I have two C's in there? I don't know. Get that out of there. Trichloroacetic acid. I don't care about the name. This is what we want. So I didn't write out the name. But here, on the left side carbon, where I have 3 hydrogen atoms as peripheral atoms, now I have 3 peripheral chlorine atoms. And over here, I bet you now realize this is trifluoroacetic acid. Okay? Acetic acid, trichloroacetic acid, trifluoroacetic acid. Well, obviously this acid and this acid can only lose this H as H plus, because that's the only H they have. Now take note. When each of these acids do their H plus giving thing, we develop these 3 anions. Do you see structurally these things are the same? Do you see that the oxygen atom, from which H left as H plus, is an sp3 oxygen atom? Actually, it's not. But with that, let me back off and say, never mind orbital electronegativity or hybridization for these oxygen atoms. Just look at them as each being oxygen atoms with 3 non-bonding pairs, a single unit of minus charge, and connected to carbon, covalently connected to carbon. Okay? Picture tells us that. Here's the real crux of this consideration. If this negative charge stays on this oxygen after this anion is developed, if this negative charge stays on this oxygen after this anion is developed, if this negative charge stays on this oxygen after the acetic acid molecule loses H plus, how will these bases compare strength-wise? How will they compare strength-wise? If this negative charge stays on this oxygen, an oxygen with 3 non-bonding pairs, a single unit of minus charge, and covalently connected to carbon. Just like this oxygen, just like this oxygen. And the carbon atom in turn appears to have a double bond to another oxygen atom, and then a single bond to a carbon atom. If this negative charge sits here, after H left as H plus, this negative charge sits here, this negative charge sits here, how will these bases compare strength-wise? How? Be the same. These bases would have the same strength, which means the parent acids would be the same strength. Now let's talk about facts. This acid, good deal stronger than this acid. Well, let's use the acids here. And this acid, trichloroacetic acid, a good deal stronger than acetic acid. Which means as bases go, This base is a good deal stronger than this base, which in turn is a good deal stronger than this base. Well, when we look at these Lewis pictures, we recognize there's only one difference of consequence, one difference period between these anionic species. 3 peripheral fluorines, 3 peripheral chlorines, and 3 peripheral hydrogens. So if these fluorine atoms can exert an electronegativity effect through the covalent bond skeleton of this species, which extends all the way to this oxygen which bears minus charge, this minus charge will be smeared toward these fluorines because of the substantial electronegativity of these fluorine atoms. Similarly, these chlorines, because of their electronegativity, will stabilize this minus charge by drawing this minus charge through the covalent bond skeleton of this anion species toward the chlorine atoms themselves. Now, what about these hydrogen atoms? You think they will exert much of an electronegativity stabilization effect on this negative charge? No. The electronegativity of hydrogen is, practically speaking, negligible compared to the electronegativity of chlorine and fluorine. So here, at least based on induction, based on electronegativity considerations, this minus charge rather sits here. Not this minus charge. This minus charge is drawn toward the chlorine atoms, which smears the minus charge. The more you smear the minus charge, it is making this thing act like a species with a larger surface than this species with respect to negative charge concentration. And here, the smearing is the best because the fluorine atoms are of greatest electronegativity. Here, by smearing this minus charge toward these fluorine atoms more effectively than smearing the minus charge from this oxygen toward these chlorine atoms, is why this thing is the weakest of these 3 bases. Induction. Interesting. Showing us that electronegativity is truly real and induction is an important effect. Interesting. So, if you're going to play this induction game, in other words, if in our bag of tricks where we've now added induction, we've got electronegativity and orbital electronegativity and stabilizing negative charge density by charge to size ratio, now induction. Does it seem that you might find it necessary, if you're going to use the induction argument, to write Lewis structures? Think that might be important? Let's go one step further with this induction stuff. Trichloroacetic acid once again. This. Versus this thing. This is trichloropropionic acid. It's just a name. I don't care about the name. What we want to recognize is that the difference between this molecule, well, I'm going to take this molecule and turn it into a base by stripping that oxygen-bound H as H+. Okay? What we want to realize is that this anionic species and this anionic species are similar in many respects. But here the covalent bond skeleton is 1 atom longer because of this CH2 group that's in this covalent bond skeleton. Between the carbon with the 3 chlorine atoms and the carbon which is covalently connected to oxygen and the oxygen where the H left is H+. So we see that the covalent bond skeleton of this anion species is longer than the covalent bond skeleton of this anion species. We have, from this argument, recognized induction to be a real property, provided in the composition and structural makeup of the species in question, you have component atoms which are of substantial electronegativity. If this anion, which has got a longer covalent bond skeleton than this anion, if the chlorine atoms on this peripheral carbon atom exert an inductive effect, an inductive stabilization effect on this negative charge, which is as great as the inductive stabilization effect exerted on the negative charge by this anion, by these chlorine atoms for this anion. How will these two compare strength-wise as Bronsted bases? If chlorine induction is the same for each, which will be the more stable, less reactive base? This one? Or this one? TCA or this one? Trichloropropionic acid. I really only put this up here to give it a label. Which will be the more stable base? This or this, if the ability to stabilize negative charge density by chlorine atom induction is the same for each, with these chlorine atoms being one atom further removed from the negative charge site, right? Because you got another skeletal carbon atom in here. If these chlorine atoms for that anion, this anion, stabilize negative charge density by induction with the same effectiveness, which of these anions will be the more stable, less reactive base? Which anion will have the negative charge smeared over the larger surface? This one. That would mean this negative charge would be diluted more effectively than that negative charge, because here you had to smear you smeared the negative charge over a longer covalent bond skeleton. Okay so far? Now let's look at the facts. Trichloroacetic acid is the stronger acid. And if the data that I found is accurate, it's a good deal stronger acid. What does this tell us? What does this fact tell us? It tells us that these atoms, which are of substantial electronegativity, can stabilize negative charge by induction only if they are close or far away to the site of negative charge development. Close or far away? Close. That's right. That's what this is about. Induction and length of covalent bond skeleton. Studies indicate that once you get these atoms of substantial electronegativity removed from site of negative charge development by 1, 2, 3 intermediate atoms, induction hardly means anything anymore. So proximity of these highly electronegative atoms to the site of negative charge density is important. You make the covalent bond skeleton too long, induction effects mean nothing or very little. All right. How about resonance? We know about resonance. Back to acetic acid, or any of these anions we've looked at so far. Do you think that resonance contributes to negative charge density stabilization by the acetate ion? There it is. The anion produced when acetic acid loses its H+. Do you think resonance contributes to the stabilization of negative charge density for acetate ion? Well, let's go back and look at this acetate ion. What additional Lewis structure can we write for the acetate ion? The other resonance form. Well, take any one of these non-bonding pairs, as this picture illustrates. They're all equivalent. And advance one to bonding status. We're moving the negative charge away from this oxygen. At least that's what the picture shows. Well, as soon as I do that, I am now imagining a double bond here. Double bond here, single bond here. And this carbon atom, like any period 2 atom, has got a maximum capacity for valence electrons of how many? 8. Period 2 atoms. 2s, single orbital sublevel, 2p, 3 orbital sublevel. That's 4 valence orbitals total. You cannot possibly have more than 8 valence electrons in the valence environment of any period 2 atom. Period. So, if we imagine this minus charge advancing to bonding status, so to speak, then we're going to go look at this presumed carbon-oxygen double bond and take one of these bonding pairs and advance it to non-bonding status. In so doing, we get the other resonance form for the acetate ion. Consequence? Not only, pardon me, well, for trichloroacetic acid and trifluoroacetic acid, not only do those anions stabilize negative charge by induction, whereas the acetate ion does not. These anions also stabilize negative charge density by resonance. Acetate ion does do that. Now let's go back to the acetic acid molecule itself. I mean, do you believe in resonance? You've heard about it. I can tell you for a fact, when I first heard about stuff like this, what the hell are you talking about? You expect me to believe this stuff? But I say again to you, there's one bottom line dictator in chemistry, in science. It's the experimentally verifiable fact. For the acetic acid molecule, how do these carbon-oxygen bonds compare length and strength? Compare in length and strength. For the acetic acid molecule, how do these carbon-oxygen bonds compare in length and strength? This bond is shorter and stronger. Now let's take away H's H+. Generate the acetate ion, where we've recognized we can write 2 acceptable Lewis structures for the acetate ion. It's 2 resonance form. How do the carbon-oxygen bond lengths and strengths compare for the acetate ion? They're equal. How about that? Just by magic. H goes away as H+, and all of a sudden, these carbon-oxygen bond lengths and strengths change. For the acetate ion, the carbon-oxygen bond lengths and strengths are identical. They're each shorter and stronger in a carbon-oxygen single bond and longer and weaker than an actual carbon-oxygen double bond. Magic. All right? So, I want you now to look at these three species. Oop. Left the minus charge off of that. I think in the statement of question 2327 in the notes, I omitted the negative charge on the bicarb ion. Take a look at what you see in the notes. I think that's the one. You see it? Did I omit the minus charge there? Put it on. That's supposed to be the bicarb ion for question 2327. Put on the minus charge. I want you to write the Lewis pictures for these three species, and then I want you to answer the question. Do these three species show resonance? Do the conjugate bases of these three species show resonance? The species themselves, the conjugate bases of these species, and do the conjugate bases of these three species stabilize negative charge density in addition to resonance by induction? Because we're now starting to put this stuff together. And this is what you'll pick up with tomorrow in discussion class. So we'll stop at this point, since I now have the exam papers